Hello, everyone. It's a pleasure to be here. My name is Pablo Jarillo-Herrero, and I'm originally from Spain, but I work already for 9 years at MIT. So today, I want to tell you a story about one of the most fascinating things going on in the world of physics and nanotechnology. I want to tell you about the construction of new forms of matter made out of two-dimensional materials, okay, and their interesting electronic and optical properties and overall behavior. Now, but before I start, what do I mean by 2D, okay? By two-dimensional? Well, I mean something that it's flat, okay? Really, really thin. Now, how thin? To sort of get a feeling for this, let's get started with an object which is a three-dimensional object. So let's take a deck of cards, similar to the one that I have here, okay? Now, these cards, you know, they have length, they have width, and they have height. So this is a bulk object. Now, imagine what happens if I take this deck of cards and now I split it in two, okay? And then I can do this again, and I can do this again. I'm going to leave them here. I can do this again, and then I end up with just one card. This is very thin. This is something which has length and width, but it pretty much has no height. So this is sort of what I mean by two-dimensional, something which has length and width, but virtually no height. Now, this card, nonetheless, you know, despite being so thin, it's very similar to the deck that it came from. Now, let's imagine I take a different 3D object, such as this apple here, and now let's imagine that I slice the apple. Chop, chop, chop. Now, I can take a slice of this apple. It's here. What do you think? Will it taste the same as the apple it came from? Yes or no? Yes, right? Indeed. This apple, this slice of apple, even though it's very thin, it looks, it feels, it tastes very much like the bulk apple it came from. In the world of two-dimensional materials that I'm going to be telling you about, the behavior is completely different. When we take one 2D object out of a 3D object, the properties change. It is like if, when you slice this apple, this little slice of apple actually tasted, let's say, like an orange. It can't change. From an apple, you slice it, and you get an orange, right? This would be very weird. Well, this is what happens, actually, when we work with materials, and we've only found about this very recently. Now, the first 2D material that we got to play with came from nothing else than the tip of your pencil, from the material that your pencil is made of. You see, this is a big pencil, okay? I got this giant pencil. At the tip, there's a material called graphite. Now, graphite is a material that consists of layers. So when you write with your pencil on a piece of paper, what you're doing is you're spreading those layers on the piece of paper. Now, let's have a close-up look at the tip of a pencil, okay? You see these crystals here? You see that they consist of these layers? You can see this layer structure already. Now, these layers that you can see here, that we're looking at with an instrument called a scanning electron microscope, these layers are still pretty thick, to be honest. Let's take an even closer look. We take a closer look at it. Now, these layers, you see very well all the structure. It looks very similar to this deck of cards, right? You can see those layers. If you could look even closer with a very refined microscope, what you would start to see is the atomic lattice of carbon atoms, you know, that these layers are made of. Now, one individual sheet of these layers is called graphene, okay? So one layer of graphite is called graphene. It looks like this, carbon atoms on a honeycomb lattice or chicken wire, and it's the thinnest material that exists in the world. It's just one atom thick. You cannot make it thinner than that. There will be nothing in the universe ever thinner than this. This is the thinnest that you can make any material. Now, it is pretty strange that, you know, this material exists, because there is a theorem in physics that says that it's impossible, that it should not exist. However, it took two very creative scientists to disregard this theorem in physics that says things cannot exist, and I'm going to try anyway. So these Scientists are here. They are Andrei Geim and Kostya Novoselov, two Russian scientists working in the UK. And in order to isolate graphene, they did something very simple. Let me actually show you. This is me, same hand. Okay? What you're seeing inside there are graphite crystals. So you put it on a piece of Scotch tape, and now you fold the piece of Scotch tape, and then you separate it. Each side of the tape sticks to the graphite, splits it into two. Very similar to what I did before with the deck of cards. Now I'm going to shift the tape, and I'm going to repeat this. And I split it into 4 pieces. Then I shift the tape again, and I do this again. I split it into 8, 16, 32, and I continue doing this until I get bored, more or less. Now, when you've done this a few times, your piece of tape looks like this. This is a piece of tape, and it has a whole bunch of graphite crystals. These are still many, many thousands of layers thick. But in there, after so much splitting, some of the graphite crystals have loose graphene sheets, 1 atom thick sheets, sort of hanging, sticking out in there. So if you take now this piece of Scotch tape, you put it upside down, and you press it on top of a substrate, something similar to what I'm doing here, and then you look with an optical microscope, it turns out that you can find isolated pieces of graphene. How does it look like? It looks like this. This is an image on your left of a 1 atom thick material, graphene, on a silicon substrate. You can see it with your eye, amazingly, even though it's only 1 atom thick. On the side, you see something which is 3 atoms thick. You can see it has a lot more contrast. Now, this is something which was extraordinary, and people were totally blown away. Just with Scotch tape and graphite, which comes from a mine, in your kitchen, you can do this. This is really extraordinary. Now, if you zoom in into that piece of graphene, and you look with a very sophisticated microscope called a transmission electron microscope, you can actually see the individual carbon atoms that make this 2D material. Each of those white spots there is a carbon atom, which is making this honeycomb lattice. This is something which was completely unprecedented. This type of work demonstrated that 2D materials exist, and therefore this theorem in physics which existed was not completely right. And it really started the field of research into 2D materials. It turns out graphene is not the only one, there are others. And this was a massive expansion of research into these material systems because they have very unusual properties. All of this, the beginning of this research led in 2010 to Andrei Geim and Kostya Novoselov to be awarded the Nobel Prize in Physics in 2010 for their discoveries. But it was really this thing, trying to attempt something which was thought to be impossible, that led to this Nobel Prize in Physics. Now, I went a little bit too far ahead. So where do I enter in this picture? So this is me in 2005, when I was finishing my PhD, all nostalgic, as you can see. By the way, I did my PhD in the Netherlands. And I was thinking, what should I do now research on? I'm finishing my PhD, what should I investigate? So my advisor comes and says, Pablo, have you heard about this new 2D material, graphene? And I was like, what? Graphene? 2D? Do those things even exist? Isn't it forbidden? So my advisor told me, no, there are these guys in Manchester who have isolated this thing. So then I thought, wow, this sounds really fascinating. So what I did is I took a flight from the Netherlands to UK, and I visited Andrei Geim and Kostya Novoselov, and I got to learn how to do this thing, which was, in the end, relatively simple, Scotch tape and graphite, right? So then when I came to MIT and I started my lab, I decided to investigate these materials because it really sounded like something very fascinating. So now, what's so special about graphene? Well, many, many, many things. Let me tell you just a few. Graphene is the thinnest material in the world, At the same time, it's actually the strongest material in the universe. It's 200 times stronger than steel. But it's also very light, because it's only 1 atom thick, and it's made of carbon atoms, which are very light. This means that even though it's very strong in this direction, it's actually very flexible in the perpendicular direction. Graphene is also so thin that it's very nearly transparent. At the same time, it conducts electricity the best of any material. So you have this material which is flexible, strong, semi-transparent, the best conductor in the universe. All of these properties have actually made many people really excited about, okay, what can we do with it? But from the point of view of physics, the thing that really we were most curious about is the fact that electrons in graphene behave unlike electrons in any other material that we know. So imagine a piece of copper is a conductor, and you can have electrons, the way electrons move through copper, they move like this, scattering, Electrons in graphene behave very differently. They actually behave closer to the way ultrarelativistic particles going at nearly the speed of light behave. So let me tell you something about ultrarelativistic particles, and in particular about light. So you know that light travels always at the speed of light, okay? Independent of the energy of the light that you're looking at. For example, radio waves, visible light, X-rays, they have very different energy, yet they all travel at the speed of light. Electrons in normal materials travel at a speed that depends what energy that electron has. So they don't behave like light at all. However, electrons in graphene travel always at a constant speed independent of their energy. And in that sense, they behave like light, but more closely, they actually resemble ultrarelativistic particles, such as those that travel through the particle physics accelerators, such as the one at CERN. This is the CERN in Geneva. Particles go through that tunnel at very near the speed of light, okay? Electrons in graphene behave very similar to those particles. They don't travel at the speed of light. In fact, they travel at a speed which is more or less similar to the speed of electrons in copper. But whereas electrons in copper go at a given speed depending on what is their energy, electrons in graphene always travel at the same constant speed independent of their energy. And that's why you can imagine graphene such as a big laboratory similar to high-energy physics accelerators where you can do many experiments related to relativistic particles. Now, these things that I said may sound a bit esoteric, so I'm going to give you an example of how different the behavior of electrons in graphene is compared to everyday objects or even electrons in regular materials. So you know that every day the physics that governs our experience are those of Newton's laws. So classical physics is governed by Newton's law. So let's take Mr. Newton here, Sir Isaac Newton. Let him have a tennis ball. And now let's put a wall in front of him. And now let's ask Newton, just throw the ball at the wall. All of you are familiar with this. What happens is that the ball bounces back at Newton. The ball cannot make it through the brick wall. That's your experience too, right? Now, when instead of tennis balls, you have very small objects, such as electrons, this behavior changes, actually. And in fact, this behavior is governed by the laws of quantum physics. And one of the main scientists that discovered quantum physics was Erwin Schrödinger. So here's Erwin Schrödinger. Well, let's put the wall. Let's give him a tennis ball. It's a smaller tennis ball than before, okay? And it's not actually a tennis ball, it's an electron, but let's represent it by a smaller tennis ball. And now let's throw it at the wall. It bounces back, it bounces back, it bounces back most of the time, but every now and then, he throws a tennis ball and shoop, it makes it through the wall. That process, which is very weird, is called quantum tunneling. It's a very common behavior for electrons. And in fact, all of our electronics, your cell phones, your computers, everything in electronics, in modern electronics, works thanks to this effect of quantum tunneling. As weird as it is, it's happening in your pocket now all the time. Okay, this is electrons in normal materials. Electrons in graphene are even weirder. They are even stranger. So, who is the main scientist that discovered relativity? Who knows? Someone? Very good, Einstein. So let's bring Einstein here, and let's repeat this experiment. We take a wall, we give Einstein a tennis ball. It's again a small tennis ball, electron, but this is going to be an ultra-relativistic electron, okay? So we throw the ultrarelativistic electrons at the wall, and shoop, 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 they always go through. They don't see the wall. They don't see the obstacle. This is actually the way electrons behave in graphene. And this is the ultimate reason why graphene is the best conductor in the world. Because when electrons go through graphene, they don't see obstacles. Shoop, 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 they make it through. If you look at a piece of copper and you look at the way electrons travel through a piece of copper, they're constantly bouncing off impurities and other things. Back and forth. Takes them a while to get somewhere. Electrons in graphene, shoop, 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 they just go through. And that's why it's the best conductor in the universe. So this is just one example of how different physical behavior, in particular this ultra-relativistic behavior, can be very dramatic and very, very different from regular materials. So graphene it was the first 2D material discovered, and people believe that it will have many, many, many applications. Because it's very flexible and it's strong, you can make flexible electronics. Because it's the best conductor, you can make high-frequency electronics. Because it is ultra thin, you can make semi-transparent electronics, things that will be transparent, but you will still be able to control electronics with it. The large surface area relative to volume, it's all surface, in fact, means that you can make batteries and supercapacitors. And because it is the strongest and lightest material, you can also use it for nanomechanical composites to make super fibers, super strong materials. Now, one of my favorite applications is one that one of my colleagues at MIT, the group of Rohit Karnik, is doing. They are using graphene as desalination membranes. So graphene is so thin, actually, the hexagons in graphene, nothing can make it through. But what you can do is you can make very small pores, very small holes on the graphene, and you can use it to separate dirty water with salt and impurities from clean water. You can make this water flow through the graphene, only the water molecules make it through, none of the dirt, none of the salt makes it through. And because it's so thin, it's very efficient at separating this water. So people believe that with graphene membranes, we will be able to desalinate water at a fraction of the energy and cost that using other technologies. And this is something that is currently under investigation. Now, I've been speaking for a while about graphene, but it turns out that this is only one of many materials now that we know in 2 dimensions. So you have a whole bunch of 2-dimensional materials that we can play with, and you can literally play with them. One of them, for example, is hexagonal boron nitride, which is shown here. Very similar to graphene, a honeycomb lattice, chicken wire, but now, instead of having all carbon atoms, you have alternating boron and nitrogen atoms. So this is hexagonal boron nitride. I should have shown you this earlier. This is graphene, okay? These are all carbon atoms here, boron, nitrogen, boron, nitrogen, boron, nitrogen, okay? Now, this material, hexagonal boron nitride, turns out to be an insulator. It's the thinnest insulator that exists in the world, less than 1 nanometer in thickness. And it's very important to have conductors and insulators to separate conductors between themselves. So these materials are also very important for technology. Do we have only these two? No, we have plenty more, actually. For example, this material, tungsten diselenide. This material is not 1 atom thick, it's 3 atoms thick. One monolayer, 1 unit cell, we say, is 3 atoms thick. From the top, it looks a little bit like graphene, or like hexagonal boron nitride. And this material is a semiconductor that, as you know, are very important for technology, for transistors and for computers. In fact, this material is fascinating because the behavior of it depends with the number of layers. For example, if you have only 1 layer, like shown here, it emits red light. If you have 2 layers, it emits infrared light. So the behavior depends with the number of layers. And that is a characteristic which is very common among these 2D materials. The behavior changes with the number of layers. I have here a very similar material, molybdenum disulfide. I'm going to pass it around so that you can see it. What you will see here in this box is some yellowish thin and another yellowish thin across. You're seeing 1 monolayer of molybdenum disulfide, a semiconductor very similar to this one, and another one across. in the area where they overlap, it's 2 layers, and it's thicker, and there is a bit more contrast. So I'm going to pass this around if you're curious, and you can see this. Now, with these materials, because they are semiconductors, they're a little bit less weird than graphene, and engineers know what to do. And even myself, as a physicist, I can do something, I can build some toy with it. So the thing that we did a couple of years ago is we created the world's thinnest LED, light-emitting diode, by using these materials, tungsten diselenide. The picture that you have here on your right is an LED shining light straight at you. And this is less than 1 nanometer. It's like if you take a sheet of paper and you divide it 1,000,000 times. Now, not only you have these 2D materials, but we can now stack them to make different types of materials. Like I can take this, I can put this on top, then I can put this on top, then I can put this on top, and now I have a material that didn't exist before, that it was impossible to make, okay? And that has properties very different from this, and very different from this, and from everything, okay? So this is really, now we can use hundreds of these materials to make millions of combinations, and this means millions of materials with new electronic and optical properties. I can do this in the various ways. I can do this one, or I can put it aside and make this one, which is a different sequence. And as you can imagine, there are millions and millions of these combinations. You know, when I'm late at night in the lab and I want to get motivated for this, I realize that this is not that different from some of my daily experience. You know, I just eat a lot of this. So, you know, if you put this together, you get a better thing, right? So that's how I see this. The last thing I want to tell you very briefly is the fact that these materials, you can also rotate these 2 layers. So you can put graphene on top of hexagonal boron nitride and now rotate it like this. You can do something like this. And you see, when you rotate it, you have a pattern that changes, a moire pattern that changes. The properties of the combination of the 2 materials depends on the angle of rotation. So now you can imagine how many of these materials we can do. In my group, we have studied this combination of materials, graphene and hexagonal boron nitride. Many other groups have done so too. Compare if we have 1 layer of graphene on top of 1 layer of hexagonal boron nitride. On the left, you have a large angle between the 2. You see the pattern of small soccer balls, which are there, spaced about a nanometer. On the right, you have a very small twist angle, and that leads to a much larger pattern. You can see the distance now between the hexagons is much larger. So with this, we have made several discoveries. It's a bit technical, and it will take me too long to explain to you, but basically, you can do things like having the best conductor turn into an insulator just by rotating the angle, for example. People think that with these materials and these combinations, heterostructures, etc., we will be able to have very interesting technology in the future. One of the closest applications will be flexible electronics, okay? Soon, meaning in something like 5 years, we expect to have your clothes with integrated electronics so that your watch, TV can be here or something like that, okay? All of these things are really possible, including things like quantum computers. One of my friends is working on an infrared camera so that you can see through fog, and you will be able to put it in your car, and you will be able to drive in the fog as if it was regular daylight without fog. So with this, people ask me often, what about the future? Who's going to do all of these things? I would tell them my young students and many, many other students and collaborators around the world that work on these materials. And the last thing I want to do is acknowledge our funding sources. This, as you can imagine, takes a lot of effort, a lot of research, and the National Science Foundation is helping us do all of this research, and this was also done in collaboration with Carol Lynn Alpert here at the Museum of Science. And I want to thank you for your attention.